Good morning to all of you. It's an honour to be able to address you as you commence the IETS TCP's Energy Future in Industry Conference. I'd like to thank Tor and the IETS Secretariat for the invitation, and I'm sorry that I wasn't able to join you in person for the event. My name's Peter Levi, and I work for the International Energy Agency Secretariat in Paris, where we examine a wide spectrum of energy system issues, particularly those relating to sustainability, security, and affordability. Industry decarbonisation is my key area of focus, and I was asked to provide a brief overview of the work we are doing on this topic at the agency. Before I get into the core content of the presentation, some quick history and background on the IEA's analysis of the industry sector. As many of you may know, we started the Technology Roadmap series looking at key sectors and technologies back in 2009. We revamped this series in 2020, providing more of a pedagogical angle and more in-depth analysis. We've since covered steel and ammonia, and the IEA's Future Of series has covered petrochemicals. More recently, we've also begun a series of country roadmaps, and perhaps of most relevance to the industry sector is the one we did for China in 2021. And we've also increasingly been working on specific policy questions for heavy industries in the context of our inputs for the G7 presidencies of Germany in 2022 and Japan in 2023. The broader energy system context for these deep dives into specific topics is provided by a modelling and analysis of the whole energy system, which is summarised in the agency's flagship publications, such as Energy Technology Perspectives, the World Energy Outlook, and the IEA's Net Zero by 2050 roadmap. All of these publications are available on our website free of charge if you'd like to learn more, and you're also welcome to reach out to me by email or on LinkedIn if you have any questions. Before I get into the details of the industry sector and the decarbonisation that sector needs to undergo, I wanted to start with the big picture, which of course is CO2 emissions from the energy system as a whole. These have risen rapidly over recent decades. Prior to the signature of the Paris Agreement, our baseline expectation was that they would continue doing so, putting us on track for a catastrophic 3.5 degrees C in long-term average temperatures. But for the first time, we are now seeing a peak in fossil fuel demand under stated policies, and therefore an associated peak in emissions. The improvements that we've seen with key technologies and policies have already shaved off around 1 degree C of projected long-term warming, compared to our pre-Paris baseline, bringing this total level of warming down to 2.5 degrees C. This is obviously a better outcome than pre-Paris, but still not enough to avoid severe effects of climate change. And the question is, can we reduce the temperature rise by another 1 degree C and keep within our 1.5 degree C limit? That will be a much tougher task. If governments follow through and implement their nationally determined contributions and their net zero pledges in full and on time, and if companies follow through on their own commitments in areas like aviation and shipping, then that takes us a long way. We recognise that this is a big if, and we cannot take this for granted, but this announced pledges scenario, or APS, puts us on track for a long-term global temperature rise of around 1.7 degrees C. But as you can see, the pathway to get emissions down to zero by 2050, thereby obtaining an even chance of limiting warming to 1.5 degrees, requires an even faster transition. I want to focus on this final scenario, the net zero emissions by 2050 scenario, or NZE, for the rest of the presentation and delve a bit deeper into what it implies for the industry sector. This is an energy system scenario for which the sources and sinks of CO2 are balanced within the energy system itself. In other words, potential sinks like in land use change and in afforestation are not used to offset emissions in the energy sector. We can see that different sectors move at different speeds on the way to net zero emissions by mid-century. The power sector is first to hit net zero by 2040 and even earlier in advanced economies. The other sector follows shortly after. Fuel transformation and direct air capture are aggregated together here. And then among end-use sectors, buildings goes virtually to zero in 2050, and relatively small quantities of residual emissions remain in the industry and transport sectors. There's around 1.5 gigatons of gross CO2 removals in 2050, which is much less than the levels of many IPCC scenarios with comparable climate ambition, largely due to the difference in gross emissions remaining in the transport and industry sectors. The difference of pace in emissions reductions in each sector is due to many considerations, but a key consideration is innovation and the current state of technology readiness for emissions mitigations options in each sector. Technologies that are available in the market today provide nearly all of the emissions reductions required to 2030 in the NZE. However, reaching net zero emissions globally by 2050 will require much more than this, particularly to tackle emissions from those areas that are often referred to as hard to abate. Specifically, the long-distance transport modes and heavy industry sectors, subsectors is what we mean by this hard to abate designation. In 2050, almost 50% of CO2 emissions reductions in the NZE come from technologies currently at the demonstration or prototype stage today. This includes a very wide range of new technologies across the various categories of electrification, CCUS, hydrogen, and sustainable bioenergy, some examples of which are shown on this slide. So I hope that provided a decent overview of the system-level transition undertaken in the NZE, and now I wanted to delve a bit deeper into the industry sector specifically. And the key overall message here is that a net zero energy system transition means achieving deep cuts in emissions across all end-use sectors, and the industry sector is no exception here. Direct emissions from the industry sector amounted to around 9 gigatons in 2021, or around a quarter of total energy sector emissions. Advanced economies account for around a fifth of industrial emissions, whereas emerging market and developing economies account for the remaining 80%. Three heavy industry sectors, steel, cement, and chemicals, account for around 70% of the emissions from the industry sector, and the emissions from these subsectors are often referred to as hard to abate, as I mentioned earlier. Part of our scenario analysis involves laying out the key milestones for the industry sector, some of which are shown on this slide. But please check out the publications I mentioned at the beginning for more details and granularity on those. Some of the milestones that are shown here speak to why heavy industries are a key challenge when it comes to reducing emissions all the way to net zero at the energy system level. Heavy industry sectors use large quantities of fossil fuels for three main purposes. Firstly, to generate high temperature heat. Secondly, for use as feedstock or raw material inputs. And thirdly, for use as reduction agents. The problem is that fossil fuels provide these energy services so well and so cheaply today, and directly substituting fossil fuels used for these purposes in heavy industries with electricity at the scale required is either impractical or expensive in most instances today. And as I mentioned on the last slide, technologies that can achieve substantial emissions reductions in the production of bulk materials like steel, cement, primary chemicals tend to be at an earlier stage of development or technology readiness than in the power and passenger transport sectors, for instance. There is one other key technical feature of heavy industries that contributes to this hard to abate designation. Their underlying physical assets tend to be long-lived and capital intensive. Here I'm talking about cement kilns, steam crackers, ammonia and methanol production facilities, but as an illustrative example on this slide, I'm showing crude steel production assets. Relative to a typical lifetime of around 40 years for these assets, we estimate that the average age since installation today is around 20 years old on average globally, and only around 15 years old in China. There's also significant clustering of the younger vintages of capacity in emerging market and developing economies, with advanced economies typically seeing older facilities that are due an investment decision in an earlier time frame. It's a very similar story for cement production assets, with an even starker split between older and younger assets concentrated in advanced and emerging economies, respectively. And China's plants are even younger, at around 11 years old on average. Without any alteration to their existing mode of operation, existing assets in the heavy industry sectors could lead to around 140 gigatons of CO2 emissions if operated until the end of their typical lifetimes. This is on a cumulative basis. As you can see, just the emissions from these assets, leaving aside any capacity additions and replacements, exceed the envelope formed by the net zero emissions by 2050 scenario and the emissions trajectory associated with that. This all paints a bit of a bleak picture when it comes to the quantities of emissions that can be expected from existing industrial infrastructure, but it's not all bad news. There are several interventions and improvements that can be made to this existing capacity, including incremental energy efficiency improvements, the blending in of low carbon fuels, and in several instances, the application of CCUS in a retrofit arrangement. The dynamics of investment cycles, whereby every 25 years or so, a plant operator will face a decision whether to renew or extend the life of key capital-intensive assets, also constitutes an opportunity. If these investment cycles are strategically considered alongside the development of innovative technologies, we estimate that around half, or around 70 gigatons, of these cumulative emissions I mentioned earlier could be avoided if low-carbon alternatives are available to replace them. Existing assets are only part of the story when it comes to achieving deep emissions reductions in heavy industries. A portfolio of mitigation options is required to achieve the 95% reduction in emissions between now and 2050 required in the NZE, including materials efficiency, energy efficiency, electrification, low carbon fuels, and the deployment of those innovative technologies I mentioned at the beginning, which account for around 60% of the emissions reductions to 2050 in the NZE for the heavy industry sectors. If we delve a little deeper into the specific categories of innovative technologies that play a role in each of these three heavy industry sectors, we can see some important differences as well as some parallels. Starting with primary chemical production, we see electrolytic production of hydrogen for use as feedstock being a key means of decarbonising large chunks of ammonia and to a lesser extent methanol production. Direct electrification of steam cracking also plays a role, but the need to retain carbon as an inherent part of the production process in the chemical industry means that CCUS technologies are attractive for capturing process emissions and alleviating the need to source large quantities of biogenic or atmospheric CO2 for feedstock purposes. In primary steel production, there's also a very important role for electrolytic hydrogen, primarily through its use in hydrogen-based DRI processes and as a blending strategy in existing process units. The innovative smelting reduction pathway, which produces a relatively pure CO2 stream, facilitating capture, is the key route among CCUS-equipped, the CCUS-equipped portion for steel shown on the slide. In the cement sector, the heavy lifting on the innovative technology front is done by CCUS technologies, whether post-combustion or pre-combustion oxy-fueling arrangements. Hydrogen and direct electrification also play a modest role here, but these innovations do nothing to address the industrial process emissions from calcination, meaning that CCUS is still required at vast scale. In all three subsectors, innovative technologies account for in excess of 90% of production of these materials by 2050. So that more or less concludes the overview that I wanted to provide today. I've focused mainly on technology, given this is a technology collaboration program event, but of course the other side of the industrial decarbonisation coin is policy. It's highly unlikely that the scale of technology transformation outlined in the slides that I've presented will take place without a strong push from policymakers to establish the necessary enabling conditions for the sector. This is increasingly the area that our member and association countries are asking us to focus on in the area of industrial decarbonisation. Our recent reports for the G7 presidencies of Germany and Japan that I mentioned at the beginning, and the strong recognition the IEA received in their communiques or the communiques for these processes illustrates this trend. The policy framework shown on this slide describes the main components of our thinking on the policy front, including the actors that need to be involved, the various tailored push and pull policy strategies that may be merited, and the enabling conditions that need to be put in place. But I've really just scratched the surface, and hopefully this presentation has provided you with some food for thought for your discussions at the conference. I wish you all a productive conference, and I look forward to seeing you in person at the next opportunity. Thank you very much.